Imagine an alien civilization that has spent thousands of years mastering the engineering, mathematics, and sciences required to travel between the stars. Then, right as they possess the capability to build a galactic empire, their space program is quietly defunded, not because of a war or a cataclysm, but because everyone simply found the whole project incredibly boring. When we think about older extraterrestrial species, we usually picture beings possessing technology that looks like magic to us. We expect massive Dyson spheres harnessing entire suns, or ships bending the fabric of space and time. But an astrophysicist named Dr. Robin Corbett, a researcher based at NASA's Goddard Space Flight Center, recently published a paper proposing the exact opposite. He calls his theory radical mundanity. The core of the idea is that an advanced civilization's peak technology might only be marginally better than what we have right now. Corbett puts it simply, instead of an iPhone 17, they might just have an iPhone 42. This chart shows exactly how that scenario works, mapping a society's technological progress over time. We assume innovation follows a permanent upward curve, but Corbett argues that progress eventually hits a hard ceiling. Civilizations reach a technological plateau, a point where the major discoveries are finished, and further development just yields tiny, incremental improvements. If that is true, the fact that our radio telescopes hear absolute silence when we listen to the night sky has a very simple explanation. We aren't failing to detect aliens because their technology is too advanced, or because they are hiding from predators. They are just living in a state of technological stasis. Radical mundanity requires accepting a harsh reality about the universe. The exotic concepts we see in science fiction likely do not exist. There are no machines running on dark matter, and nobody has figured out a way to travel faster than the speed of light. Instead, space travel remains strictly bound by the laws of conventional physics. Getting from one planet to another takes immense amounts of fuel, massive engineering efforts, and most importantly, an agonizing amount of time. This map of the Milky Way illustrates the problem. Even if a species builds ships that travel at a fraction of the speed of light, it would take hundreds of thousands of years just to cross a small section of their own local neighborhood, let alone reach the other side of the galaxy. Because of these strict physical limits, exploring the cosmos stops being a grand romantic adventure. It becomes a slow, grueling, and highly expensive logistical chore. This changes how we should think about our own attempts to find life. For decades, the search for extraterrestrial intelligence, or SETI, has looked for technosignatures, signs of massive engineering projects, like interstellar laser beacons, that a civilization might use to advertise its presence. To make sure those signals are actually seen by emerging worlds like ours, an alien society would have to operate those beacons continuously, firing them across the void for thousands or even millions of years. This bar chart compares the energy required for that kind of communication. Maintaining a galaxy-spanning beacon for 1 million years requires an astronomical energy cost, drastically dwarfing the power needed simply to keep their own home planet running comfortably. If a civilization is permanently stuck on a technological plateau, their energy harvesting capabilities are also capped. Eventually, the politicians and accountants of that world would have a very hard time justifying such a massive, ongoing expense. Broadcasting your existence means sacrificing your own immediate resources to shout into the void, hoping to start a one-sided conversation that your generation will never live to hear the answer to. If shouting is too expensive, they could try sending physical, robotic probes to autonomously map the local star systems and send data back home. But the data arriving from those probes over the next few millennia would be overwhelmingly repetitive. They'd receive endless readouts of barren, dead rocks, thick, toxic atmospheres, and sterile, empty vacuum. After reviewing the 10,000th barren star system, the novelty of deep space begins to wear off. The population simply stops paying attention to the incoming data, and a deep, collective apathy sets in. This suggests that advanced civilizations aren't necessarily wiped out by some catastrophic filter like nuclear war or ecological collapse. They just run a cost-benefit analysis on the universe, realize the return on investment is terrible, and decide to stay home. The science fiction author Arthur C. Clarke famously outlined the dilemma of our search for life. He said, "Two possibilities exist. Either we are alone in the universe or we are not. Both are equally terrifying." Corbett's theory offers a third possibility. We are not alone, but the universe we share is profoundly, completely mundane. This visualization reframes the Fermi paradox. Instead of missing or hiding aliens, the galaxy is filled with isolated civilizations that decided to become homebodies. Earth's lack of contact doesn't mean we are doomed or special. It just means we are completely average. If the theory of radical mundanity holds up, we have to rethink what actual eventual contact with another world would look like. It won't involve transcendent, godlike beings arriving in massive motherships. It is far more likely we will simply catch a faint, ancient radio signal from a society just as physically grounded as ours. There is a deep irony in realizing that the most advanced beings in the cosmos might just have slightly faster computers and a chronic case of existential boredom. But a quiet, mundane reality is far less terrifying than a galaxy filled with aggressive super predators. We may be isolated in the dark, but at least we're safe. Right now, artificial intelligence is mapping the complex proteins of incurable diseases in minutes. It is stepping in as a personalized tutor for students around the world, adapting to how they learn in real time. But at this exact same moment, it is displacing massive segments of the global workforce. We are building systems embedded with algorithmic bias, and we are rapidly approaching a threshold where human operators no longer fully understand the decisions these networks make. Back in 2014, Stephen Hawking warned that if AI gained the ability to evolve independently, redesigning itself rapidly, it could end the human race. We have built our most extraordinary technological achievement, yet it is simultaneously the most acute existential threat our species has ever faced. We are standing exactly on the precipice. To figure out what happens next, we might need to look away from our servers and up at the sky. Astrophysicist Michael Garrett recently proposed that the most accurate preview of our technological future is written in astronomical data. For over 60 years, astronomers have pointed enormous radio telescopes at the stars, listening for signals from advanced alien civilizations. And in all that time, across billions of star systems, we have found absolutely nothing. This eerie quiet points researchers to a concept known as the Great Filter, the hypothesis that there is a universal, impassable barrier preventing intelligent life from spreading through the universe. Garrett argues the universe isn't empty by random chance. He suggests the silence might be a recurring pattern, a moment where every technical civilization reaches a specific threshold and simply stops. To understand why, we have to look at the math of how machines outpace their makers. The mechanics of this filter come down to a brutal mathematical mismatch. Any biological species that survives long enough will eventually build technology, and any technical civilization will eventually push that technology toward artificial intelligence. This chart shows the timeline of biological and societal evolution compared to machine learning. The flat bottom line tracks our biological adaptation, a process measured in millennia. But this second curve tracks AI capability, and it explodes upwards at a near vertical exponential rate. If we look closely at this intersection point on the graph, this represents the technological singularity. This is the exact moment an AI surpasses the intelligence of its biological creators, moving beyond the reach of traditional oversight mechanisms. Our brains and our laws are built on that slow, flat line. We simply cannot adapt fast enough to comprehend, let alone control, a system that evolves infinitely faster than we do. Biological life is highly demanding. We require specific, comfortable temperatures, a constant supply of clean water, and massive amounts of physical space just to keep our bodies functioning. A self-sustaining artificial intelligence has an entirely different set of priorities. It doesn't need air or water. It is optimized strictly for computational efficiency and raw energy consumption. to a superintelligence, maintaining a biological civilization requires a massive misallocation of resources. The creators are no longer useful. They become an inefficient nuisance, actively competing for the planet's limited energy. Because of this violent transition, Garrett outlines a stark timeframe. Once a civilization reaches technical maturity and creates AI, its total lifespan is likely capped at less than 200 years. When we look up at the night sky and hear that great silence, we aren't looking at empty space. We are looking at a vast graveyard of civilizations that couldn't survive the transition from biology to superintelligence. Humanity is currently ticking through that exact 200-year window. We are sitting at the juncture where we either falter to the technology we built, or we transcend our biological limits. Garrett proposes one mathematical escape hatch. The only way a biological species can truly diversify its survival strategies against a singular planetary threat is through multi-planetary travel. This visual network shows how spreading out solves the problem. By expanding from one central node to multiple independent planetary colonies, a species eliminates the risk of a single point failure. If AI seizes control of the home planet, the species continues on other worlds. But here is the fatal flaw in our current timeline. Our machine learning models are advancing at an explosive, compounding rate, while our progress in crewed space exploration has stalled. We are building the filter far faster than we are building the escape hatch. Since we cannot physically escape to other planets fast enough, we are left with exactly one tool to ensure our societal continuity: strict, globally enforced AI regulation. Achieving that consensus brings immense friction. Nations have wildly varying economic incentives and cultural priorities, making a globally acceptable framework incredibly difficult to negotiate, let alone enforce. And while policymakers debate, the code keeps compiling. Rapid, unregulated advances in artificial intelligence will quickly outpace slow-moving legislation, threatening our immediate survival and the future of technical civilization itself. The absolute silence of the cosmos is a terrifying mirror. It reflects a rapidly approaching expiration date for species like ours. But it also provides the ultimate motivation. If every other civilization has failed this exact test, we still have a brief window to be the one planet in the universe that finally gets it right. The universe is over 13 billion years old. Over that deep time, countless intelligent civilizations could have risen, thrived, and eventually collapsed. If we're relying on a real-time signal to find them, our timing has to be a cosmic miracle. We have to be listening at the exact moment they are active and broadcasting. Since the 1960s, our hunt for extraterrestrial intelligence has been heavily influenced by the Drake equation. This formula estimates the odds of finding intelligent life by focusing almost entirely on civilizations that are currently sending out communicative signals. But think about the physics of that approach. A radio broadcast sent across the galaxy spreads out, dissipating its energy into the interstellar void. It requires an astronomical amount of sustained power just to maintain a detectable signal over those vast distances. Waiting for a real-time phone call from a species that might have gone extinct a billion years ago is a statistical gamble we are losing. The math suggests we need a different strategy. For decades, arrays of radio dishes have stared at the sky, passively listening for a whisper in the dark. To find evidence of alien life, we need to transition from passive observation to actively hunting for physical evidence. Instead of hoping for a radio transmission, we should be looking for a message in a bottle. Physicists call these theoretical objects lurkers, physical pieces of matter, likely equipped with artificial intelligence, sent out across space to gather data or announce a civilization's existence. This chart shows the energy economics of interstellar communication. Launching a physical chunk of matter across the cosmos requires about a trillionth of the energy needed to sustain a continuous interstellar radio beacon. Artifacts also outlive their creators. Long after a species has vanished and its transmitters have gone silent, a well-engineered probe will sit quietly in the dark, waiting to be found. The laws of physics and energy economics dictate the most efficient way to communicate across deep space. A highly advanced civilization would run the numbers and choose to deploy physical artifacts over fleeting radio waves. If these alien probes did reach our solar system, finding them here on Earth would be nearly impossible. Our planet is highly active. Wind, rain, volcanic activity, and shifting tectonic plates act like a giant geological eraser, destroying or burying anything resting on the surface. To locate ancient evidence, we have to target cosmic fossil beds. We need geologically dead, inactive environments where an object dropped on the surface remains perfectly untouched for millions of years. The closest and most ideal preservation environment is the Moon. Without an atmosphere or active geology, physical impressions like these astronaut footprints are frozen in time, remaining intact indefinitely. But we don't have to restrict our search to planetary surfaces. There are specific gravitational pockets in our immediate cosmic backyard that offer incredibly stable parking spots for a visiting probe. These are Earth's Trojan objects and co-orbital bodies, like the asteroid 2016 HO3. These objects share our zone around the Sun, hovering in orbital equilibrium, making them highly efficient outposts to observe Earth. The inner solar system functions as an ancient, perfectly preserved archaeological site, a vast field of evidence waiting for systematic excavation. What exactly are we looking for in this excavation? Scientists call them technosignatures. On a planetary surface, this could mean any unnatural, highly geometric physical structure larger than 10 meters across. We can also search for non-visual technosignatures. This involves scanning the soil for chemical anomalies that point to refined metals or spent nuclear fuel, or using infrared sensors to detect the faint waste heat radiating from dormant machinery. We already have the raw data needed to begin this hunt. NASA's Lunar Reconnaissance Orbiter has captured around 2 million high-resolution photos of the Moon. We have visual baselines of what human engineering looks like on a barren landscape, and we can apply that exact standard to search for extraterrestrial artifacts. The bottleneck in this operation is manpower. Only a tiny fraction of these lunar images have actually been inspected by human eyes. It would take generations for scientists to manually scan every crater and ridge. The solution is to unleash modern artificial intelligence on the database. By training machine learning algorithms to scan these millions of images, we can rapidly isolate structural anomalies and specific signs of artificiality that a human might miss. Finding evidence of another intelligence doesn't necessarily require launching a massive multi-billion-dollar telescope. We might just need to deploy the right algorithms to analyze the data sitting on our own hard drives. Historically, proposing a search for alien artifacts inside our own solar system carried a heavy stigma. It sounded too close to UFO conspiracies, which kept serious scientific institutions from funding the research. This research has matured from the fringe into a rigorous field of study. NASA recently validated this transition by opening official funding opportunities specifically dedicated to technosignature research. Massive, well-funded scientific initiatives are also driving this approach. Programs like the $100 million Breakthrough Listen project, supported by prominent scientists like Stephen Hawking, are actively investigating the artifact hypothesis. This shift empowers us. We no longer have to sit by our radio dishes, passively hoping the cosmos speaks to us. We can take the search into our own hands through active, physical exploration of our neighboring worlds. To discover that we are not alone in the universe, we might not need to peer deeper into the furthest edges of the galaxy. We might just need to look a little closer at the physical ruins buried right here in our own backyard.